We are going to discuss today a very interesting thing which is known as indicator function. Actually, we know how to define a set function. That is, it is defined over a set, and that set belongs to some space or some field or sigma field or class of sets that has been generated from a particular space or a big set, and this is a real valued function. So in most cases we assume that it's a non-negative function. But we have seen that there are many actually set functions. The most common is the probability function or any measure defined on a particular measure space. But the interesting thing is that the simplest possible set function is known as indicator function, which takes only two values, 0 or 1, depending on whether at which place the element belongs to or which set the element belongs. But the thing is that there are very interesting properties that this indicator function holds, although it is very, very simple, and it has some nice relationship with other general set function, as for example the probability function. So today we are going to discuss first we would like to define an indicator function. What is the meaning of an indicator function, how it is defined, and at the same time we will study few of its properties which might be useful in studying other set functions, other more general set functions. And it is interesting to note, it will be clear immediately within a few minutes, that this other set functions, mainly the probability function, has some kind of relation with the indicator function, or it can be studied, or many theorems in probability theory can be proved very, very easily using simple indicator functions. So we are going to discuss a few combinatorial results mainly related to probability theory that will come as a consequence of set theory. So our objectives is that first I would like to define an indicator function. That means the definition of an indicator function, how does it look like, and a few examples. And then we will discuss a few very common theorems in probability using indicator functions, a few properties and few results we are going to discuss. But first, what is an indicator function? Suppose omega script f and p be a probability space. Since we will finally try to investigate the relationship between, or how to develop a probability theorem or probability result in terms of indicator function, so here we are going to define indicator function with respect to a probability space. So the definition goes like this: IA of omega or W on big omega is an indicator function if IA omega equals to 1 if omega belongs to A, and 0 if omega belongs to A complement. That means capital A is a big set that belongs to the sigma field script f, and we define indicator function either it takes the value 1 or 0 if omega belongs to A or A complement respectively. So it's a very, very simple function, probably the simplest possible function that one can have. Now a few properties of indicator functions. So it is clear that an indicator function can take only two values, either 0 or 1, no other values it can take. So the first property is very simple, that is IA squared. That means if I multiply IA with IA, I will get IA. The proof is again very simple, because if omega belongs to A, then IA would be 1, and naturally IA squared would be 1. On the other hand, if omega belongs to A complement, IA would be 0 and IA square would be again 0. So IA square equals to IA always. I of null set, that is phi, is always 0. And I of big omega is always 1. This is intuitively true, because a small omega, an outcome, an element, must always belong to a particular set, and that set is always a subset of big omega. So any point that we can consider is always belongs to big omega. So I of omega is always 1. And phi means there is no such point. So no point belongs to any set, or any point belongs to phi. That means there is no such point. So I of phi is 0. Now what about slightly more complicated things, but ultimately it will come out to be very, very simple. That is, if A is a subset of B, this will imply and implied by I of A is less than equals to IB. Now the proof is extremely simple, just following the standard notations of results in set theory. We can always write any set B as A intersection B union of this in A intersection B with a complement intersection B. Now if omega belongs to A intersection B, then of course IA equals to 1 and at the same time IB equals to 1. That means IA omega equals to IB omega equals to 1. Because if omega belongs to A intersection B implies that omega belongs to A, that means IA equals to 1, and similarly omega belongs to A intersection B implies omega belongs to B, that means IB equals to 1. On the other hand, if omega belongs to a complement intersection B, IA would be 0. Of course IB is 1, but IA would be 0 because omega belongs to a complement. At the end, since omega belongs to B, then IB equals to 1. So IA equals to 0, which is strictly less than 1 naturally, and which is in fact IB. So in this case, IA is less than IB, strictly less than IB. So if omega belongs to a complement intersection B, that is one part of B, then IA would be less than IB. But omega belongs to A intersection B, that is another part of B, then IA equals to IB equals to 1. So taking together, we can immediately write that IA less than or equals to IB. And naturally the converse is also true. Now this gives us an idea that we have one result very similar to this result in probability theory, which says that if A is a subset of B, then that will imply probability of A less than equals to probability of B. We will see this proof later on. Now let us consider another property of indicator function with respect to A complement, and the property is I of A complement is nothing but 1 minus IA. Again, the proof is extremely simple. That is, if omega belongs to A complement, IA complement is nothing but 1. Because omega belongs to A complement, and by definition of the indicator function, IA complement equals to 1. Now we can write 1 as 1 minus 0. Now if omega belongs to A complement, then naturally I of A is 0. Because I of A is 1 if omega belongs to A, and I of A equals to 0 if omega belongs to A complement. So we can write IA complement equals to 1 minus IA if omega belongs to A complement. Now what about the other part? That is, if omega does not belong to A complement, that means omega can belong only to capital A. Then again, by the definition we have by definition of the indicator function, I of A complement is 0 because omega does not belong to A complement. And 0 means we can write 1 minus 1, and the second one is nothing but I of A because omega belongs to A, so IA equals to 1. So what we have, A complement equals to 1 minus IA, and this is true when omega belongs to A complement as well as when omega does not belong to A complement. So taking together, we have the proof that I of A complement equals to 1 minus IA. Now what about indicator function over intersection of two sets? That is, I of A intersection B equals to IA into IB. The proof again goes exactly in the same way. That is, I of A intersection B equals to 1. That is implies and naturally implied by omega belongs to A intersection B. This implies and implied by that omega belongs to A and omega belongs to B, because both should hold in order to belong to A intersection B. And this will implies and implied by omega belongs to A means IA is 1 and omega belongs to B means IB equals to 1. So IA into IB equals to 1. So what we get is that I of A intersection B equals to 1 implies and implied by IA into IB equals to 1. Now indicator function here, it takes so this proof is complete but only for the value of 1. So we have to prove the same thing for the value 0. That means when this indicator function takes the value 0, and if we follow the same logic we can easily see that even for the value 0, I of A intersection B equals to IA into IB. So this proof is complete. So now it is probably clear that we are moving on to finding any result related to indicator function which is defined on the union of two sets. Now that part is also simple, we will come back to that, but before that let us discuss its connection of the indicator function that we have discussed for the last few minutes, its connection with the probability theory. Now, as we already mentioned that we have started with the probability space, which is omega, script f and p. Omega is the big set full sample space, script f is the sigma field generated by the class of subsets of omega, and p is a probability measure defined on omega and script f. And for any set A belongs to script A, we can treat IA of omega, for omega belongs to A, as a random variable. Because now A belongs to script f and we have defined the probability measure, so this is the probability space. So we can easily define we can treat IA of omega as a random variable. Then if we take expectation of IA, so expectation of IA is what? 1 into probability that IA takes the value 1. Now IA takes the value of 1 means omega belongs to capital A, that means just probability of A, plus 0 into similarly probability of A complement, which is nothing but probability of A. So thus we have a nice relation between the probability of any event with the expectation of an indicator function defined on that event or on that set. So probability of A can always be written in terms of expectation of I of A. Now let us do a few quick proofs. One is probability of A union B equals to probability of A plus probability of B minus probability of A intersection B. Now we all know the proof of this result, because we can just look at the Venn diagram and split A union B into union of few disjoint sets and then apply the axiomatic definition of probability and we will get the proof. But here I am going to prove this result using the indicator function. Now note that indicator function over A union B is IA plus IB minus I of A intersection B. So also note that I have not proved this result, so I just leave it to you to prove it. The proof goes exactly in the similar logic, following the similar logic for the proofs of the other results on indicator functions. So if we take this for granted that I of A union B equals to IA plus IB minus I of A intersection B, just take expectations on both sides. That means we have expectation of I of A union B equals to expectation of IA plus expectation of IB plus expectation of I A intersection B. Now we know that expectation of an indicator function is nothing but the probability of the set on which the indicator function is defined. So naturally expectation of I of A union B equals to probability of A union B equals to expectation of IA means probability of A, expectation of IB means probability of B, and expectation of IA intersection B means probability of A intersection B. So you see here the proof is extremely simple, just one or two line proof without any splitting of the events or any Venn diagram kind of thing. So natural question is, can we prove similar kind of results in probability theory using indicator functions? Answer is yes, in most of the cases, probably if not in all the cases. So next one is probability of A complement is equals to 1 minus probability of A, and we have already seen that I of A complement equals to 1 minus IA. Again take expectations on both sides, so it will be expectation of I A complement equals to expectation of 1 minus IA, which is nothing but 1 minus expectation of IA, and which in turn means that probability of A complement is equals to 1 minus probability of A, because probability of A complement equals to expectation of IA complement and probability of A equals to expectation of IA. So we have already proved two things. Now let us see whether we can go for the big proof of Poincaré's theorem, the famous Poincaré's theorem, which deals with the probability of union of n events. And we know that Poincaré theorem is probability of union AI equals to 1 to n is summation I equals to 1 to n probability of AI minus summation I less than j probability of A intersection AJ plus up to dot dot plus minus 1 to the power n minus 1 probability of A1 intersection A2 intersection AN. Now, before this proof, first note or recall De Morgan's law on sets, which is union of AI equals to intersection of AI complement and whole complement, or that means complement of intersection I equals to 1 to n AI complement. And recall two small results on indicator function. One is I of A intersection B equals to IA into IB, and I of A complement equals to 1 minus IA. Now you see, these are the two simple results on indicator functions that we are going to use in order to prove the big Poincaré theorem, which looks complicated but also very elegant. Now we start with indicator function. We are supposed to prove union of AI, probability of union of AI. Let's start with the indicator function, where indicator function is defined on the union of AI, union of these sets. So I of union AI, I equals to 1 to n, we can write 1 minus I of intersection AI complement, because we know that union AI is a complement of intersection AI complement, and indicator function of a complement of a set is nothing but 1 minus indicator on that set. So it is 1 minus complement of that set. Now we know that indicator of intersection of two sets equals to product of the indicator functions defined on individual sets, and we can extend this for many other sets, so that intersection of AI complement and indicator function defined on that is nothing but product of the indicator functions defined on each of these sets. That means it becomes 1 minus I of A1 complement into I of A2 complement into up to I of AN complement. Now again apply the same result, that I of A complement equals to 1 minus IA for each of these AI complement. So this becomes 1 minus IA A1 into 1 minus IA2 into 1 minus IAN. Now in a school level elementary algebra will give you, so if we consider the product of all these n terms involved in the second term of the expression, then 1 gets cancelled and we are left with summation IAI minus summation I less than j equals to 1 to n IAI into ij, that means pairwise product, then product with taking 3 at a time and so on. The last term will be minus 1 to the power n minus 1 IA1 IA2 IAN. Again apply this result, I of A intersection B equals to IA into IB. So what we get is summation IAI I equals to 1 to n minus now IAI into IAJ equals to I of AI intersection AJ, sum over that, and so on. The last term will be I of A1 intersection A2 intersection up to AN. So the proof is almost complete, except that we have to take expectations on both sides. So if you take expectations on both sides, we are left with probability of union of AI equals to 1 to n, which is nothing but expectation of I of union AI equals to expectation of summation IAI minus summation I less than j, summation over I less than j, I of AI intersection AJ, and so on. And we can take expectation inside the summation sign, because it's a finite expectation, expectation of a sum of finite terms. So summation I equals to 1 to n expectation of IAI, which is nothing but probability of AI. Second term is summation over I less than j equals to 1 to n expectation of AI intersection AJ, and this becomes probability of AI intersection AJ. The last term expectation of I of A1 union A1 intersection A2 intersection up to AN is nothing but probability of A1 intersection A2 intersection up to AN. So this is actually the Poincaré theorem. Initially, if you recall, usually we prove Poincaré theorem using the induction, but here there is no need of induction, using induction in this case. Simple results on indicator functions will give us the elegant proof of this Poincaré theorem. So for the last few minutes we have discussed indicator function, we have defined it, we have studied few properties, mostly in terms of like what is indicator function of a complementary set in terms of the indicator function of that particular set, or indicator function defined on union of two sets, how it is related to the individual sets, indicator functions defined on individual sets or the intersection of the two sets. But the most importantly, we have seen that the few theorems in probability can also be proved very easily, effortlessly almost, using indicator functions or the properties of indicator functions, and those properties are very obvious. And even we have observed that that big, little complicated looking but very elegant theorem due to Poincaré, the probability of union of say k events or m events, this theory usually we have proved using induction, but using indicator function it's a few lines proof, we can prove it in few lines. And remember that in this proof we have used only very simple properties like union of or rather indicator function defined on A intersection B equals to product of the indicator functions defined on A and B, and also indicator function defined on A complement is nothing but 1 minus indicator function defined on A. So this very simple thing, and also the De Morgan's law we have used, this very simple results lead to the proof, naturally very easy proof of the original Poincaré's theorem. So this gives us an idea that in future, in many areas, or mainly in probability theory, many theorems we can prove using indicator functions. Or if we encounter any problems in probability or to prove something in terms of sets in probability theories, probability of different sets, we can at least try. We can start with indicator function and see whether we can prove it very easily.